Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last time, where we were looking at the mutual inductance between the stator windings and the rotor windings. So in this week we will continue with this concept, and I will talk a little more about how we can quantify the impact of, or rather quantify the linkage between the flux produced by the stator as it links with the rotor. So as always, before starting this lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses which you can access on my own website, which is pythonpowerelectronics.com. So this is the home page of this website of my project. And if you go to, if this is the home page, there are these 4 buttons which will take you to the main contents of this project. And one of these buttons is called Learn. If you click on this button, it will take you to the list of courses which I have currently. So I have 5 courses as of now, and the very first course I have is called Simulating Power Electronic Circuits Using Python, and in this I talk about the basics of how you can use Python and Python Power Electronics to simulate basic power electronic circuits. The second course I have is called Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and packages such as the SciPy package, or rather the signal package within SciPy, to design and analyze filters for power engineering applications. The third course I have is called Simulating Magnetics for Power Electronics Using Python, and in this I talk about how you can use Python and Python Power Electronics to model and simulate magnetic components such as inductors, coupled inductors, and transformers. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and packages such as the Python Control package to analyze and design controllers for power engineering applications using the specific case of a single phase inverter connected to a single phase grid. The very last course I have is called Why Specialize in Power Electronics, and this is a free course which is targeted towards junior undergraduate students or even high school students in order to tell them about the challenges and opportunities available in power electronics so that they can choose this as their domain of specialization. So these courses are available as of now on 2 platforms, which is Decibels Labs and Udemy, and if you click on any of these buttons, it will take you to the link for the course. The link of this page is provided in the description of this video, so if you're interested, please do check out the description of this video. So with this, I'll get back to my lecture. So if we go back to our flux diagram page and a little bit of recap as to why we are doing this, we can go back to the Excel sheet where I had described the concept of mutual inductance. So when we talk about mutual inductance, what it means is how is the flux produced by one coil linking with another coil and which is magnetically coupled with the first coil. So if you have coil 1 and coil 2, we can say that if we calculate the flux produced by coil 1 as the ampere turns of the coil divided by the reluctance of the flux path, and we calculate the flux linkage of this flux with respect to coil 2, then we will get the flux linkage of coil 2 produced due to the flux produced by coil 1. This is mutual flux, right? This is mutual flux as opposed to the self flux which we had calculated before. So we are now looking at mutual flux, and if we come back to the diagram, I had talked about how we can consider a simplified stator winding. That is, typically the stator windings are distributed all across the circumference of the stator. But in reality, we can, for the purpose of analysis, assume it to be just 2 slots diametrically opposite each other, and the coils are wound on this slot. And the same for the rotor as well. Even if we have a squirrel cage induction motor which consists of bars that are short circuited, we can assume that all these bars are essentially just 2 bars, or rather 2 pairs of bars, 2 collection of bars, which are diametrically opposite each other on the circumference of the rotor. So now we were looking at the flux produced by the stator and how it links with the rotor. So if we come back to our usual diagram, we see that, for example, if we have the flux produced by the stator, and that we know to be in this direction. So for example, and here maybe I can just draw a quick diagram that let us say that we have a coil, right? So I'm going to draw a coil. Again, it's not going to be very nice, but the purpose is just to again, very bad coil, but try to imagine that this is an actual coil. And if this coil were to carry a current in this clockwise direction, right? Okay, now it looks really bad, so I'm going to delete it. Terrible. I could draw a slightly better one, I suppose. Maybe I can use an ellipse instead. Yeah, that looks better. That looks like an actual coil. Okay, so if I were to say that this is a coil, right, and this coil were to carry a current in the clockwise direction, then from our knowledge of magnetism, and if we use the right hand thumb rule, we know that because if the coil was to flow in the clockwise direction, if we were to look at the coil from this direction, from the right to the left, then in this case, the face of the coil where the current is flowing in the clockwise direction becomes a south pole. And because it becomes a south pole, the flux lines enter this coil. So these are all entering because it's the south pole. And if we were to look at this coil from the other direction, that is from the left to the right, then because if we are looking from the left to the right, the current were to be flowing in the coil in the counterclockwise direction. And because it is flowing in the counterclockwise direction, that face of the coil, when we are looking from the left to the right, becomes the north pole. And therefore the flux will be leaving the coil, right? Always remember, flux flows out of the north pole and into the south pole. So this way, we can say that this is how the flux is produced. Of course, this flux will then come over here and complete. Again, terrible drawing, but sorry, this is as good as it gets. Drawing was never one of my strong points, so you have to use your imagination while following with this lecture. Of course, I would always suggest take a piece of paper and try to draw it on your own. But the purpose why I'm trying to draw this coil is that if we were to say that this stator coil was something similar to this, that is, if this we can assume that there is a coil which is wound around the stator because this is a cross section, then in that case the flux were to be flowing, the net flux of this particular coil would be from the right to the left. And that's what we've drawn here. This line with an arrow indicates the net flux produced by the stator. And since the stator is not rotating, this flux is in this direction, but because an AC current is flowing in the stator, this flux will change from a 0 value to a positive value, back to 0 again, to a negative maximum and back to 0. This is how it is if there is an AC current flowing in the coil. And therefore, this AC flux, which we have shown in this direction, will be also following the same AC path. That means it will be at one point 0, which means there will be no flux at all, and this will increase from 0 going up to a certain maximum, which means it will be a strong flux along this horizontal line. It will go back to 0, being no flux at all, and then it will go down in a negative direction, which means that the flux will reverse, will flow from the left to the right, reach a certain maximum and go back to 0 again. So this flux also follows an AC path going from the right to the left, back to 0, and from the left to the right, and so on and so forth, as in the same way as the current follows an AC cycle. So now that we have this description, the question is, how do we quantify this association of the stator flux with the rotor? So as it is quite obvious that this flux produced by the stator is linking the rotor flux. So I'm going to just get rid of this diagram and delete it. Okay. And now what I'm going to do is I'm going to start drawing another few more coils that resemble this rotor. So for example, let me just see if I can draw. If I were, and this is a simple case, maybe I start with this first. If I say that this is the rotor, right? This is a rotor which is unenergized, and I want to know that if there is a certain flux, such as the stator flux, how will it associate with the rotor? So for example, if I were to draw this stator flux from the right to the left, or the left to the right, doesn't really matter, and I were to say that this was passing through the stator, right? And it is quite obvious that when I'm talking about a net stator flux, in reality I'm talking about something like this, several stator flux lines which are passing from the right to the left or the left to the right, either way, because it's an AC flux. And therefore it is quite obvious that because this rotor coil is aligned in such a manner vertically, right? Vertically along this axis. So if I can draw a certain axis, let me just draw. I need a straight line. This is probably a straight line. So if I draw this vertical axis and say that this is my vertical axis and this coil is along this vertical axis, as it is quite obvious, in such a case, the associate, or rather the linkage of the stator flux with the rotor is extremely high. Alright, one can even go so far as to say that if we neglect any stator leakage flux, all the stator flux is linking with the rotor, right? Now the question then arises, what are the other possibilities that are there? So for example, let me see if I can delete this one rotor and now draw a rotor in this direction instead, right? So now the rotor axis is actually 90 degrees away from the vertical axis of the stator, right? So this rotor is now aligned. So these rotor bars are now aligned diametrically opposite each other along the horizontal axis, right? Now, it is quite obvious that this rotor is actually horizontal. You have to imagine this rotor to be exactly horizontal, right? Because this is a representation in 3D, is horizontal, and these stator flux lines are also horizontal. What this means is that the associate, or the linkage of the stator flux with the rotor in this position, when the rotor is horizontal, is minimal. Maybe this is a little misleading. Let me just draw a slightly slimmer rotor. Yeah, this is probably a little better indication of what I'm trying to do, right? So I have made this very slim to indicate that this is actually horizontal, right? So imagine there is a slight depth, and that's only because I'm trying to show it 3D, but in reality this rotor coil is horizontal, and therefore it's quite obvious in this state that there is almost zero linkage of the stator flux with the rotor. Now let's look at some other examples. Let me just delete this and let me see if I can draw. No, I can't. So I have to use freehand. Okay, let me try. I'm always terrified when I try to draw. Okay, this looks not too bad so far. Okay, looks more like a potato, but imagine that this is a rotor coil, right? This is a rotor coil that is inclined something along this axis. It's just not vertical, it's not horizontal, right? It's something at an angle such as this. So you can say that the angle of the rotor with respect to the vertical axis is some non-zero angle, right? It's not 90 degrees either. Now the question then arises, what is the linkage of this stator flux with the rotor coil? This is between those two cases. It is between the case when it was vertical, when there was maximum linkage, and when it is horizontal, when there is almost zero linkage. This is somewhere in between. So now the question then arises, how do we quantify this linkage? Because we have to quantify if we have to come up with a mathematical model that we can use to simulate this machine. So now the question then arises, if I were to have such a coil, let me just draw this. Maybe I copy it better than trying to draw it again. Can I copy? Yes, I can. And paste it here. Very good. And let me grab this, pull this down. So if I were to have such a rotor coil, and supposing now I were to say that this rotor coil was energized, right? If it was carrying a current again in the clockwise direction, how would the flux be in this rotor? What flux would this rotor coil produce? If I were to ask this question, then quite obviously this rotor coil will also produce a flux in exactly the same way as the stator would have produced. Same logic. Since it is in the clockwise direction, this face becomes a south pole, and therefore flux lines are providing in this direction, right? Flux is entering the coil and it is leaving the coil from the other side, right? So what would be the net flux? The net flux would be similar in this direction. right? Sorry, in this direction. So therefore one could say that we now have a net flux which is flowing in this direction. And how would we quantify this direction? This direction is exactly 90 degrees from the axis of this rotor. That is how we would describe it. So if we measure a rotor axis, we can say that the stator flux is 90 degrees with respect to the rotor axis. Which means, in this case, if I were to try to draw it, I could just copy this line. Is that the line? Apparently it is. Yes. And let me move it here. So I would then ask the question that if the rotor was to be energized, how would the flux be? And the flux would be in this direction. But in reality, the stator flux is horizontal. And therefore, if we say that the stator flux is horizontal, but the rotor would have produced another flux, then in that case, we know that the flux that links, that is, if the stator flux that links with the rotor will not be exactly equal, will not be 100%. Right? If this rotor flux were exactly aligned to the stator flux, then we can say that the linkage between the stator flux and the rotor is maximum. If the stator flux was 90 degrees to the rotor flux, then we can say that the linkage between the stator flux and the rotor is minimum. Right? Is minimum. Whereas in this case, we now have something in between. And what is that in between? That is the angle that is made. So for example, here if we draw, let me just copy this line. Apparently that is a line. Let me copy it. Yes, it is. And let me paste it here. So if this axis of the rotor was to make some angle, let's say theta or whatever, gamma, whatever we want to call this. If it was to make some angle with respect to the vertical axis, then this rotor will make that same angle with the horizontal axis. Right? Let me just draw that as well. So the same, let me move this and align it with these two. The centers have to coincide. Well, they are almost coinciding. So it's just basic trigonometry. If I say that this angle of the rotor axis with respect to the vertical axis was to be some angle theta, then that same angle, let me just draw it here, this same angle would be made with the rotor flux with respect to the stator flux. The same angle. I don't know what's wrong with this. Yeah, okay. This is probably should be deleted, and let me draw another one. Yeah. So this is the same angle. So now this rotor is rotating at a speed omega. Let me go back to the Excel sheet. This rotor is rotating at a speed omega, resulting in an angle, rotor position angle theta m. Right? If we say that at any instant of time t, this was the theta m angle produced, then we know that the same angle is the angle between the stator flux and the rotor flux, or would be rotor flux. So then the question arises, can we express this stator flux in a manner such that it would be, what would be the stator flux that would fully link with the rotor? This is the question we need to ask. And quite obviously, if we take a projection of the stator flux with respect to this theoretical rotor flux, then in that case, that new projected stator flux will be the flux that completely links with the rotor. And therefore, quite obviously, if I come back here and I say this, I can say that this flux 1 multiplied by N2 is the flux that would be produced normally, right? When the flux is in that, when the rotor is in that vertical position and the stator is completely linking, stator flux is completely linking with the rotor. But otherwise, in other conditions, I would say that the actual flux is a cosine of the rotor position angle theta m. Right? If we assume, of course, the assumption we are making here is that this angle is rotor position angle is the angle that is made with the rotor axis by the rotor axis with respect to this vertical axis. We can define it in different ways. There are several different ways in which we can define these. This is just one possible definition. So if we make this definition, we can say that this flux multiplied by the number of turns of the rotor multiplied by the cosine of this theta m is the actual flux linkage. Right? So I could write this as psi 2. This is the real psi 2. And therefore, quite obviously, this mutual inductance is this psi 2 divided by I1. Right? Now, it is very clear that the mutual inductance is a function of the rotor position angle. And this is something which we can quantify. Right? We can quantify it by saying that this mutual inductance between the stator and the rotor is equal to some maximum value. Right? We can write it as some MSR max multiplied by cosine of theta m. Right? Where this MSR max is equal to flux into N2 divided by M1. Is equal to psi I 2, or rather let me just write it out, flux 1 multiplied by N2 divided by I1. This would be the expression. And of course we can even expand this even further, like flux 1 is equal to N1 divided by N1, N1 divided by I1 into reluctance. And we've already talked that how we can calculate the reluctance, or rather approximate the reluctance of the flux path. The approximation of the reluctance of the flux path is merely this reluctance of the air gap which is along the radii. We've talked about this before. So in this manner we can come up with an expression for MSR max. So here we have now said that for a squirrel cage induction motor, we know MSR is dependent on theta m. We also know that this MSR is a cosine function of the rotor position angle. So therefore we can now expand this out and write it as an expression of the rotor position angle. With this, for a squirrel cage induction motor, we have now included the rotor position angle inside our mathematical model. So this is a huge breakthrough. Why? Because until now these equations, which were the electrical equations, had no component of mechanical in them. It appeared like this appeared almost like the equations of a transformer. But in reality this is not a transformer, this is an induction machine. And if this were to be an induction machine, we have to take into account the fact that it is rotating. Which is, we have to take into account either the speed or the rotor position angle, one of them. Now we do have that expression. We now have the expression which says that this MSR, let me write this at MSR, that this MSR can actually be written in this manner. That is, it can be written as a function of a maximum mutual inductance multiplied by the cosine of the rotor position angle. So now that we've achieved this, we can now combine these two equations and say that this equation is now dependent on the rotor position angle. And now this is truly the equation of an induction machine. Now going further, of course, we now have to find an expression that varies this rotor position angle. Because remember, as of now, this rotor position angle theta m is some mysterious angle. But instead of some mysterious angle, we have to come up with an expression for the angle itself. And that angle will come from equating the electrical torque, the mechanical torque, and the rotor position angle. And this we'll talk about in the next few lectures, because we now have to describe how the torque is produced, how this electrical torque is produced, what is the mechanical torque, and how one can come up with the concept of how the difference between these torques results in the angular acceleration. And once we have that, we now have the complete mathematical model of the induction motor. So with this, I'm going to end this lecture as it's already gotten pretty long. If you have any doubts, you can send me a message either on social media or send me an email, whichever is your preference. Otherwise, I will see you next week, where we will start talking about how torque is produced in an induction motor, or for that matter, any mutually coupled circuit, right? We don't have to start talking about machines right away, because I'd like to take again a slight detour into basic physics and talk about how torque is produced due to magnetic fields. So, thank you again for watching and see you soon. Goodbye for now.